For several weeks, astronomers, physicists, and space enthusiasts have been divided over a single question. Was the object known as 3I Atlas merely an interstellar comet or something far more extraordinary, perhaps even an alien probe? Debates intensified, theories multiplied, and the anomalies observed only added to the tension. The discussion seemed to be heading toward a deadlock, until the James Webb Space Telescope revealed new data. At first, it was believed that these findings would finally settle the controversy. The explanation presented was elegant, coherent, scientific. Yet, as the details were examined, something didn't quite fit. The proposed answer solved part of the puzzle, but raised as many new questions as it answered. And when one looks closely at what is being defended, it becomes clear that there may be much more behind this story than the public has been led to believe. According to the official narrative, 3I Atlas is an interstellar comet with an unusually rare chemical composition, the result of billions of years of exposure to galactic cosmic rays. This natural processing would have altered its chemistry in predictable ways within the known laws of physics. It was, therefore, a simple and elegant explanation, the kind of solution science tends to favor, an exotic phenomenon explained by known mechanisms, only on a colossal timescale. But when one starts to examine the details of this hypothesis, things become more complex than they first appear. What first drew attention was a chemical feature almost impossible to reconcile with the normal behavior of comets. 3I Atlas shows a carbon dioxide to water ratio of 7.6 to 1. For comparison, comets in our solar system have an average ratio of only 0.12. In other words, Atlas contains about 63 times more CO2 relative to water than any typical comet. Statistically, this discrepancy is so extreme that it lies more than 4 standard deviations above the observed mean, a difference practically impossible to occur by chance. When these measurements were published, even the most cautious scientists could not immediately explain what they were seeing. Only later did a hypothesis emerge that would become the official explanation. The object had been profoundly altered by billions of years of cosmic ray bombardment as it traveled alone through interstellar space. The study supporting this idea was led by Roman Madiolo of the Royal Belgian Institute for Space Aeronomy. He and his team combined James Webb observations, data from the SpaceX mission, laboratory experiments, and radiation transport simulations. Their conclusion was straightforward. 3I Atlas was not a pristine remnant preserving untouched traces of its parent system, but rather an object deeply modified by radiation over cosmic ages. The interpretation is theoretically sound, well-grounded physics supported by real experiments. Yet, it also contains weaknesses that warrant careful scrutiny. Observations made by the NIRSPEC spectrograph aboard James Webb on August 6, 2025 were rigorous. When the object was 3.32 astronomical units from the Sun, detailed measurements showed exactly how its composition manifested. The explanation offered was that cosmic rays had converted carbon monoxide into carbon dioxide, forming a processed outer layer about 15 to 20 meters thick. This irradiated crust would account for the anomalous abundance of CO2. Indeed, laboratory experiments show that when water and CO ices are bombarded by energetic particles, CO2 is produced. The process is well documented. Yields vary with ice thickness, mixture ratio, particle energy, and temperature. The problem, however, is that in these experiments, CO is never completely consumed. Typically, chemical equilibrium stabilizes when the CO to C ratio reaches about 0.1, far from what is observed in 3I Atlas. Even under prolonged irradiation, CO tends to reappear as complex organic molecules break down. This means that if 3I Atlas had truly been processed by billions of years of cosmic exposure, its chemical ratios should be balanced, not display the absurd excess of CO2 we observe. The researchers' response to this inconsistency was that highly specific initial conditions or additional processes not yet replicated in the lab could explain the deviation. In other words, the hypothesis remained valid, but only at the cost of new assumptions. And this is where a chain of adjustments begins to accumulate, making the explanation increasingly convenient, yet less and less likely. Another issue arises when analyzing the depth of processing caused by cosmic rays. Radiation transport models indicate that only the outermost layers, up to about 20 meters, are significantly altered. The deeper material should therefore remain nearly pristine, preserving its original composition. If the surface crust is the only processed part, then as the object approaches the sun and begins releasing gases, we should observe a stable composition as long as erosion affects only that layer. But once erosion exceeds 20 meters, the release of primitive material should radically change the observed ratios. That prediction is testable. Erosion calculations indicate that before perihelion, material loss was small, less than a meter, meaning still within the irradiated crust. However, as the object moves closer to the sun, the erosion rate increases and may eventually cut deeper than that processed layer. If that happens, measurable changes in gas chemistry should appear. If the proportions remain constant even after erosion reaches the interior, the irradiated crust hypothesis collapses. That would mean the anomalous composition is not superficial, but intrinsic to the entire body, something no natural model can convincingly explain. The authors of the study acknowledge this possibility and attempt to reconcile it by suggesting that Atlas might have undergone specific events, such as close stellar encounters or collisions that mixed its outer and inner layers. Thus, processed material could have been redistributed, creating the appearance of a homogeneous composition. These are plausible hypotheses, but they rely on a series of highly unlikely coincidences. Skeptics of the natural explanation see a familiar pattern: the accumulation of assumptions to sustain a hypothesis that would otherwise collapse. First, we accept that cosmic ray processing was far more intense than any experiment suggests. Then, we imagine a resurfacing event that was very recent but not too recent. Finally, we assume finely tuned temperatures and exposure durations to produce the observed color and chemistry. Each element on its own seems reasonable. Together, they form an improbable narrative. The color of 3I Atlas adds yet another mystery. Its spectrum is a deep, intense red, among the most extreme ever recorded in solar system bodies. This hue is attributed to the formation of dark organic compounds after long periods of radiation exposure, which makes sense. However, the degree of reddening in Atlas would require irradiation doses and conditions at the very upper limit of what models allow. Again, a possible but exceptional scenario. Moreover, it is known that color also depends on temperature during irradiation. For Atlas to acquire this color naturally, it would have had to be irradiated at a very specific and constant temperature for billions of years, another unlikely coincidence added to the list. It is important to say, the cosmic ray processing hypothesis is legitimate, scientific, and coherent. The problem is not its physical foundation, but the number of exceptions required for it to fully fit the data. When a theory depends on multiple special conditions that must all occur simultaneously, its statistical plausibility drops sharply. And even if the chemical explanation holds, it does not solve the other anomalies associated with 3I Atlas. Of the 9 identified by Avi Loeb and other researchers, 8 remain unanswered. The near-perfect orbital alignment with the ecliptic plane, the anti-solar jet of ejection, its enormous mass compared to Oumuamua, the absence of iron in its metallic emissions, the bluish glow observed at perihelion, the atypical polarization pattern, and, perhaps most intriguingly, its directional coincidence with the mysterious WOW radio signal. None of these features are explained by the cosmic ray hypothesis. It solves only one piece of the puzzle and ignores the rest.
In the coming months, new post-perihelion observations may decide the fate of this theory. If 3I Atlas's composition changes as it moves away from the Sun, that will confirm the idea of a processed surface crust. But if the chemical ratios remain constant, the model collapses, and we will have to consider the possibility that the object is fundamentally unlike anything we know. Madiolo's paper ends with a revealing line. Interstellar objects cannot be treated as pristine messengers from their systems of origin. They are, rather, natural laboratories for studying the effects of cosmic rays on matter. It is a profound shift in perspective, and also a convenient way to avoid more uncomfortable questions. If all interstellar visitors are modified by radiation, then we can never be certain whether any of them are natural or artificial. So far, we know this much. 3I Atlas has an extraordinarily anomalous chemical composition. Cosmic rays can alter icy substances over billions of years. Experiments and models support this possibility. But we also know that the explanation requires highly specific conditions, does not address other anomalies, and still awaits confirmation from future observations. The history of science shows that convenient hypotheses have often been overturned. Meteorites, once denied as stones falling from the sky, were eventually confirmed. Continental drift, mocked for decades, became the foundation of modern geology. Even ulcers, long attributed solely to stress, turned out to be caused by bacteria. In every case, consensus held firm until the evidence became undeniable. Perhaps 3I Atlas is exactly what they say it is, an interstellar comet processed by radiation. Or perhaps it represents something deeper, a clue that the universe is more complex and perhaps more inhabited than we imagine. For now, we wait. The object continues its silent journey through space, moving away from the Sun and carrying with it the 9 anomalies that still defy logic. Soon, telescopes will observe it again, and the data will tell us whether our natural explanation holds, or whether we must admit that something truly extraordinary passed through here. The universe, after all, does not care for our preferences or the comfort of our certainties. It simply is. It is up to us to observe, to question, and, above all, to have the courage to face the answer, whatever it may be.